So this is our second lecture on psychrometrics. We've been into ideal gas mixtures, but the study of moist air, it's our second lecture. Last time we talked about three temperatures. What are those three temperatures? The dry bulb, wet bulb, and dew point. And then also we talked about two humidities, the relative humidity, which was a ratio of mole fractions, but essentially because everything behaves as an ideal gas, it's a ratio of the actual vapor pressure of the water in the mixture. So it's the partial pressure of the vapor in the mixture divided by the maximum that it could be, which was the saturation pressure of water at that dry bulb temperature. So PV over PSAT. And then the other humidity, which was omega, a Greek omega, what was that humidity? Absolute humidity, which was a ratio of the mass of vapor in the mixture to the mass of air. Usually we think of it mass per unit volume to per mass per unit volume, but it's just kilogram per kilogram. Kilogram of vapor per kilogram of dry air. So I should have put a D on that, emphasize dry air, because sometimes you get confused. Kilogram of vapor per kilogram of the mixture? Nope, kilogram of vapor per kilogram of only the dry air. So a lot of times it's dimensionless. If you wanted to calculate it, you'd typically use the equation 0.622. Where did that come from? Molar mass of the vapor, the molar mass of dry air, times the partial pressure of the vapor in the moist air mixture, divided by the partial pressure of the dry air. Well, sometimes they'll write it as 0.622 PV over P minus PV. What is that P without a subscript right here? Total pressure of the mixture, room pressure. Okay. Now, once we're armed with these things, we can start making calculations. We won't get into any system analysis today, but we're moving in that direction. So we have room air. It's at a given temperature of 29 degrees C. Which of those three temperatures is 29 degrees C? Did they give us the dry bulb, wet bulb, or dew point? That's right. Dry bulb, 29 degrees C. And 97 kilopascal, what is that? Total pressure, 97 kilopascal. The partial pressure of the water vapor is given. PV is equal to 3.364 kPa. That's kind of a funny piece of information given to you, but hey, this is just a beginning problem. That's what's given. It's kind of rare that you would actually be given that, but calculate the partial pressure of the dry air. How do you do that? I'll take a volunteer from over here. So you know that the total pressure is the dry air plus the vapor pressure. So just what you said, the dry air pressure is the total minus the vapor pressure. We calculate that. We find it's not 97, it's 93.6. All right? You would keep all those digits in your calculations. If this was the final answer, you'd round it off to 93.6 kilopascal. Part B. Part B says, calculate the relative humidity. What symbol? Phi in this textbook for relative humidity. And somebody over here, tell me how you're going to calculate the relative humidity. Yeah, so we know that dry bulb temperature is 29, so we can look up, this is data from the table. To save you time going into the table, I reproduced and said that at this temperature, this is the saturation pressure. So you get PSAT at the dry bulb temperature, and we have that the relative humidity is PV over PSAT. The actual vapor pressure is 3.364 kPa. We divide it by 4.009 kPa, and we're left with the relative humidity. Does that look good? Relative humidity is around 84%. All right, press forward. All right. Same conditions, same information, same table of data summarized here. Calculate the dew point temperature. How about somebody not in the first two rows on this side, but anywhere over there? How do I calculate the dew point temperature? Or I'll tell you what, I'm going to pause. Everybody work on it. When I get 2 or 3 answers correct, written down like this is the strategy for calculating it, then I'll press forward. All right, what I'm looking for is somebody to say temperature, our subscript is dP for dew point, I forget what the textbook actually uses, is equal to, and you said that it was 26 degrees C? How did you get 26 degrees C? Which is the correct answer? So basically the dew point is I get the partial pressure of the water vapor in the moist air mixture. You know what? We were given that in the problem statement. And then I look for the temperature such that the saturation pressure is precisely that partial pressure. And that temperature then is called the dew point temperature, isn't it? And so this was a made-up problem. So you just you don't have to interpolate, you just look until you find, haha, there it is. Hence the dew point. Meaning I can cool that moist air until I get to 26. If I try and cool it to 25, what's going to happen? Some of that water vapor will not be in the vapor. A lot will still remain in the vapor, but some will condense, turn into liquid, and collect in the bottom of the container. What happens if I cool it to 24, 23, 20? More liquid's going to condense in the bottom of the container. All right. Calculate the mass of water vapor if you had a volume of 1 cubic meter. Give me the equation for that. If you have a calculator, you can run it, but I'm more interested in the equation. Well, what equation would you provide to calculate the mass of water vapor in 1 cubic meter volume of that moist air? So the hint I give is that it always behaves as an ideal gas, and so you can write something like PV is equal to mRT, where we're talking about the partial pressure of the vapor, we're talking about the mass of the vapor, and the gas constant for the vapor. Does that equation look good? Do I need to put a subscript V on the T? No, don't do that. How about on this? Do I need to find the partial volume occupied? No, it's double counting. Dalton's model, the concept of partial pressures filling the total volume of the mixture, of the ideal gas mixture. So you could write that the mass of the vapor is equal to the partial pressure of the vapor, the volume of interest, 1 cubic meter, divided by R the vapor T, or a lot of times I'll write it PB. V is equal to the molar mass of the vapor divided by R bar T. Yes?
Is that temperature just the temperature of the room, or is it like a dew point?
No, that's the dry bulb temperature, because the gas is at that temperature. Yeah, you need it in Kelvin. But when we substitute, I hate to belabor anything too much, but the partial pressure of the vapor, 3.364 kilopascal. The volume, 1 meter cubed. The molar mass, 18.02 kilogram per kilomole. Then the R bar, 8.314 kilopascal meter cubed per kilomole Kelvin. And then the temperature is 29 plus 273. If you want to put more digits on it, great. 273.15 Kelvin. And then you just cancel all your Kelvin, kilomole, meter cubed, kilopascal, left with the unit of kilogram. And the answer is 0.0241 kilograms. Am I going to have a hard time picking that up? No, it's going to be a hard time even sensing it. Like, how much is it? So I like to do this, I'll say if somebody has a water bottle, Show me something with a kilo, mass. And a lot of times a water bottle's half a kilogram because it's half a liter, 500 milliliter. What's that say on your water bottle? How much volume is that? Is that 500 milliliter?
Yeah, 591 milliliter.
All right, a little bit more, but you could shake that, get a good sense of it. And so that would be half a kilogram. We're talking about 0.024. That's not much mass, but that's the answer that we're looking for. All right, let's press forward. What is the humidity ratio? What is the symbol that I'm asked to solve for? Omega. Omega is my humidity ratio. And then how am I going to solve for it? Should I give you a few seconds? Or, Professor, you're doing such a good job of explaining things, just keep right on going. Which one? Give you a second or two? Keep on going. All right. 0.622, partial pressure of the water vapor over the partial pressure of the dry air. Guess what that was? Guess what that was? And away you go. And it's 0.0223. Any units on this, omega? Or could I put 0.022, left out a 0, 0.223 and box it and call that the answer? You could. You definitely could. What number? Yeah, that's the ratio of the molar mass of vapor divided by the molar mass of dry air. Yeah. All right, so we have a different problem now. We have air at 100 kilopascal. It's atmospheric pressure, close enough. 30 degrees C, pretty warm. 84% relative humidity. All right. Calculate the dew point temperature and the humidity ratio of that air. What is the dew point temperature and humidity ratio? So here are the table of data so you don't have to look them up. All right. So how are we going to calculate that dew point temperature? Yeah, temperature, dew point. You look for this, the saturation pressure that gives us the exact current partial pressure of the water vapor in the mixture. So what's our current partial pressure of the water vapor in the mixture? Relative humidity times Psat at the dew point? No, at the dry bulb. Dry bulb, that's right. So we would say, okay, the relative humidity is 84%. And the saturation pressure at the dry bulb of 30 is 4.247 kilopascal. So you get that value. And then you have to come down here and look for it. And maybe you have to interpolate to find out the dew point temperature. In the interest of time, it comes right in at 27 degrees C. All right? All right. So then what is the humidity ratio? 0.622 times that partial pressure vapor divided by total pressure minus the partial pressure vapor to get the dry air pressure. And that'll come in 0.026, or 0.023, sorry. This is a leader for the next page for another problem, okay? So do we understand those two values? Now the question is say, okay, this is what you just solved for. You said it was the dew point of 27 and humidity ratio 0.023. Now the air is cooled at constant pressure. So the pressure is not going to change. It's going to stay 100 kilopascal. I'm going to cool it a little bit. You cool it from 30 degrees down to 29. Not a whole lot of cooling. Just 1 degree C cooling. You lowered the temperature. Then you're asked questions. Say, okay, at that new lower temperature of 29 degrees C, calculate the relative humidity, phi, calculate the dew point temperature, dP, and then calculate the humidity ratio, omega. But before we launch into numerically calculating those, answer the questions qualitatively. Look at the relative humidity that is at 30 degrees C. It was 84%. the new relative humidity at the lower temperature of 29. Will that new relative humidity be greater than the other, the beginning point relative humidity, or will it be the same, or will it be less? Do you understand the question? Yeah, all right. All right, let's, should I talk about it and then re-vote? How about this? I'll come back and grade that one. What does the dew point temperature do? It was originally 27 degrees C. The air was at a dry bulb of 30, but I'm going to cool it to 29. The dry bulb's now at 29. But what about the dew point temperature at that new condition? Is it the greater than 27? Is it the same as 27? Or is it less than 27? Hopefully that's not too confusing of a question. I'm going to give you a little extra time. A little over a minute. Talk to your neighbor. Everybody get in? All right. Well, before we grade that one, let's try this one. The humidity ratio. Okay, what was the symbol for humidity ratio? Omega. What is the description of it? Ratio of the mass of vapor to the mass of dry air in that moist air mixture. That's what it's equal to. How does that change? So if I cool the moist air down to 29, it used to be 0.023. Will it now be greater than 0.023, the same as 0.023, or less than? Humidity ratio. Do you want a minute? There. All right. Hopefully everybody got in. How can the mass of vapor in our moist air be increased? How can that happen? You add water. All right. In this room, is there anybody adding water to the air in this room? If you're alive and you're exhaling, you're adding some water. You are. If you're sweating, you're even adding more water. But even if you're not sweating, your skin is still, giving water into this room. If I had a coffee pot, would it give water in the room? Absolutely. If I have a drink or a beverage that's open, I know that your water bottles are sealed, but yeah, that would be giving water. If I had a stove that was baking or cooking or something, and typically boiling water, something, it's adding water. How do I increase humidity ratio? Add water. How do I decrease the humidity ratio? Well, I get rid of water. How do I decrease the amount of water in air? You get it cold, and then it dews out. That is the strategy. Now, you can put it over something that like a desiccant, that likes to gobble up and attach the water to it. And you'll see those little packets of desiccants, like don't eat this, in your package of new shoes that you buy, right? Anybody ever been tested to say, well, I wonder what it tastes like? It says don't eat, but I'll see what it, don't do it, don't do it. But you can get rid of the water vapor out of the air by passing it over a desiccant as well. All right. What about the mass of dry air? How can you increase in the moist air mixture, the dry air, the nitrogen, the oxygen? Really, not really anyway. I mean, you could. How about decreasing it? Is it going to condense? You're going to spray in liquid dry air and then it adds to the air? No. So basically there's no changing there. So what did you do when you cooled it from 30 to 29? Did you some way upset the balance between vapor and air? Only if 29 is less than the dew point temperature would you have started to condense. But what do you suspect the dew point temperature is? 27. Did you start to condense any water vapor? All right, so now I pose this last question again. The humidity ratio. Will it be the greater than, the same as, or less than the original humidity ratio? All right, let's go ahead and grade it, right? Do you think it's 100% correct? Not even close. Not even close. So anyway, what we're going to find is that you did a lot better the second time we approached the question. True? Because this is the first time. Right? But these concepts you're learning, right? You're improving. Do we want to go ahead and grade the dew point? Or do you want to rephrase it or redo it? Just grade it and move on? Or what do you think the dew point temperature does? Do you want to grade it or not, or redo it? All right, just grade it. Stays the same. Until you hit the dew point temperature in the cooling process, the dew point temperature is just going to remain the same temperature. It did. What about the relative humidity? Let's go back to relative humidity. Let's redo this question right here. What does the relative humidity do? Is it greater than when it's dropped the temperature? Did it increase? Or did it remain the same, or did it go down? Is it less than? All right, everybody in. Okay, let me do this. If you did cool all the way to 27 degrees C, such that it's now the dry bulb equals the dew point temperature. And we already know then that it's also equal to the wet bulb. All three of those temperatures are the same. What would be the relative humidity if I was able to cool it all the way to 27? Now, I know I stopped at 29, but if we cooled it all the way to 27, what would be the relative humidity? Would it be greater than 84? It would be 100%. It would be saturated air, right? So guess what's going to happen? Okay, I cool it from 30 to 29 to 28 to finally 27. Do you see the pattern? What did it do? It increased. So the relative humidity at 29 degrees C is higher than it was. It's higher than 84. True? Did I do it right? You don't know? I'm going to go back to it right now. You were right before I added the confusing explanation. All right. Oh, you missed it? Yeah, I actually retarded learning. That's terrible. All right, let's press forward. Well, now that we have an intuitive sense of where they're going, give me the numbers. Give me the numbers. What is that relative humidity when you cool it from 30 to 29? How much larger is it than 84? Is it 90, 95? What is it? Can you calculate that percent? And then what is the dew point temperature? Well, we already did that one. It's going to remain same at 27. And what about the humidity ratio? It'll remain the same. So really only one of these needs to be numerically calculated. What's that new relative humidity? So let's pick it up here. So the new relative humidity will be the vapor pressure divided by that saturation pressure, Psat, at the current dry bulb temperature. And so this partial pressure is going to be the relative humidity, which is that we started with, 0.84, times the Psat at 30 degrees. And then what you do is you divide that by Psat at the lower 29 degrees. And so we get 0.84, and then you'll see, oh, the Psat at 30, that's over here, 4 4.247, and the PSAT at 29.009, and that ratio then gives you the little boost up. And so the relative humidity goes up to 89%. All right? All right. Let's press forward. Ready to do this again? Well, you cooled it from 30 to 29. So the initial temperature was 30, but you cooled it to 29. What did the relative humidity do? Well, it was 84. Now it went to 89. What did the dew point do? Didn't change. I didn't hit the dew point. What did the humidity ratio do? Didn't change. I didn't change the balance between the vapor and the dry air. The masses are the same. But somebody says, keep going. Cool it to 28. What do you think happens? Who would like to help me on either box A, B, or C? You just tell me which box you have confidence in. This is the answer. Okay, you've got your hand up. You think A is 94? You already did it? He's fast. But you know what? Somebody help with B or C. B is 27. Why don't you go for the easy one? It's like I say, drive to Houston. You're going to say, first I'm going to get on the road, go to El Paso, then Wichita Falls, then Oklahoma City, then New Orleans, because I want to go there too. And then finally over. You took the hardest one. All right, who would like the next easy one, C? Who can do the C? You got it? It's 0.02301. All right, so you got this one. I gotta ask my questions better. All right, now if you drop to 27, that's where you're going. You're dropping to 27. Now, what do you think relative humidity? Who would, not of the three that participated, who would like to do answer A on this one? You would. Guess what? He's right. All right, you're out of the game. Who would like to do the temperature dew point? 27 is correct. And who would like to do omega? Unchanged. Now we're getting to something now because we hit the dew point. If you go lower, if you drop the temperature, what will happen to some of the water vapor in the moist air mixture? It will turn into liquid and condense. You have so much experience with this. So now, who would like to do this one right here? Yes. It'll be 100%. It'll actually, if you didn't think about it, you just calculate, it'll be like 103 or 4%. You say, oops, I made a mistake. It's going to be saturated air and it's 100%. So you're all out. What do you got for the next one? 26. What about the dew point temperature? 26? Good. Real good. All right. Now, what about the omega? It's a little bit of work, isn't it? Because isn't some of the vapor going to be gone out of the moist air mixture? Is omega going to be the same, higher, or lower? Lower. You're lower. It drops a little. All right. Last group. 3 new students participating. Who would like to participate? All right. 100%. You got the easy one. Good job. How about this one? It's going to be 25. It's saturated air. You continue to wring a little moisture out, but it stays saturated as you continue to cool. And then this one will be lower, right? And the numeric value is hard to know. You'd have to calculate it. All right. I don't think I have time for this problem. So in the interest of time, we're done for today. And guess what? Plenty of time to walk over and listen to Dr. Creamy. Thank you.